Hey, good morning, all you MRWC fans. We're in Theme 1, Section 3, and we've gone through Section 3B1, all right, talking about the constructions, how to construct, all kinds of irrational numbers like root 2, root 3, root 5, and combinations of those things through sum and differences and things. And so, yeah, that was pretty challenging. We talked about the distance formula. We used the Pythagorean Theorem heavily, and we're going to get into a little recap on the distance formula and Pythagorean theorem, and also radicals and certain things, and get you guys ready for the next activity here in 3B3. All right, so this is a 3B1, 3B2 recap. So 3B1, all right, and 3B2. Whether or not you've gone through 3B2, which is a distance form of Tarsia. That's an optional game, and so some instructors might have given that to you, some instructors may not, depending on the situation, especially here in distance learning online format. So that may or may not be possible to do the distance Tarsia in an online format, depending on where you're located, so and what the technology capabilities are. So it doesn't matter. You should have gone through the distance formula, at least the Pythagorean theorem, and some dealing with some roots, radicals. Okay, so let's go for it here. One of the important things in MRWC is structure, being able to see the structure between problems, whether you're using the distance formula or the Pythagorean theorem. So, for example, what am I saying by structure? Let's highlight that because that's a major concept in this section, because now we're going to get into the numerics. Okay, I'm talking about the numbers, number sense. All right, and so in order to see the structure between the problem, what am I talking about? So, for example, when finding the distance between the points, so read with me. So, finding the distance between the points, all right, these A and B right here, all right, instead of using the distance formula multiple times, all right, we're going to draw the right triangles and notice the structure and similarity between them. All right, so we're not going to use the distance formula. All right, do not, and don't work ahead either, do not use, all right, the distance formula right now. All right, because I want you to see something else. So work with me. Don't work ahead. Just make a little note. I said instead of doing that, all right, draw the right triangle. This is what we want to do. We want to draw a right triangle and notice the structure and similarity between the triangles. So here we go. So just draw some simple pictures with me. So what we're going to do is we're going to plot these points. So x-axis here, y-axis 0, -1. So we're going to go down 1 unit. So 0, -1 is right here, point A. All right, -1, comma 0. -1 right here is point B. All right, and we want to figure out the distance between A and B. So let's draw the right triangle. So by the way, get out a red pen. So if you don't have a red pen in your note taking, always take notes in 2 colors, okay? Pencil and some colors. So get a red pen out, or purple, or pink, whatever your favorite color is, orange. All right, annotate your notes really well and do a good job with that. Now, notice that this is a perpendicular, these are perpendicular axes. So we have a right triangle here. And notice it's isosceles, right? This leg is 1, and this leg is 1. And notice, and if you've been around in all my previous activities here, previous to all of this, you know this is an isosceles right triangle, okay? So then it's isosceles, it's isosceles right triangle, all right? The legs are 1, which means the hypotenuse is root 2. So this is 1, 1, root 2, isosceles right triangle, where the legs are 1 and the hypotenuse is root 2. Now let's take a look at the next one here. Notice that I'm not using even the Pythagorean theorem right now. We learn from the past. We know this, all right, from the past. An isosceles right triangle with the legs equal to 1 gives us a hypotenuse of root 2. You should know that. So I'm going to write down we know, all right, from the past. Now let's take a look at the second one here. Let me draw that a little bit better. Okay, so x-axis, y-axis here. Now let's say that this is all 1 unit high. So 1 unit, 1 unit, 1 unit. And then, notice it's equally spaced, by the way. So space them out equally. It's not perfect, so let me make it a little bit better. Okay, that's better. Okay, so make it equally spaced 1 unit, and let's draw the next right triangle. So 0, comma 1/3. Okay, 0, comma 1/3. So you have to divide it up into 3 equal spots. And so right here, there's A, right there. B is negative 1/3, comma 0. So you have to divide it up into 3 equal parts. And there's B. And there's my little right triangle in there. So now the sides are 1/3, and this little side right here is 1/3. So, and that's B right there, okay? So let me put A over here so you can see it better. Okay, we don't want to do that. So I'm trying to get rid of that letter A there. Okay, there you go. So what should the hypotenuse be? This is the structure part, the similarity in the structure part. So let me highlight that. So understanding what you know about this first right triangle here, can you determine what the hypotenuse is, given the fact that it's another isosceles right triangle? But in this case, the legs are 1/3. The legs are 1/3 of the previous triangle. Okay, so the scale factor, if you want to talk about scale factor right here, this is from geometry right now. So the scale factor, all right, is equal to 1/3. This is 1/3 as long in all the dimensions or the lengths or the side lengths. So predict what the hypotenuse would be. So the sides on this one here, they're instead of 1, 1, root 2, it would be 1/3, comma 1/3, comma what? Well, it's going to be 1/3 of the previous one. So again, the hypotenuse on the previous triangle was root 2. So the hypotenuse here would be root 2 divided by 3. It would be 1/3 of it. All right, you can prove that too, by the way. So this would be root 2 divided by 3. And notice I didn't use the Pythagorean theorem. I didn't use the distance formula. I'm using basic common sense, looking at the structure and the similarity between the triangles. Okay, and that's an important part of MRWC. So don't take this for granted. Stay, keep your focus hat on, meaning pay attention. Okay, so let's draw another one now. Okay, so in this one here, so let's scale the axes here. So 1, 2. All right, 1, 2. Scale equally on both axes. All right, -1, -2 here. And then down here, -1, -2. All right, so you scale the axes equally. That's important. So you don't have to, but to see the similarities, you probably want to do that. So -2, comma 1, be point A. And then B is 1, -2, so write 1 down 2. So write 1 down 2, point B. Okay, and here's your right. And you draw the right triangle. Okay, there we go. So there's your right triangle. All right, so what are the distances here? So, I don't know why it's doing that. So from A to C, all right, it's 1, 2, 1, 2, 3 units. 1, 2, 3, down 3 units here. So it's, oh my gosh, this is another isosceles triangle. So it's another isosceles right triangle. All 3 of these are isosceles right triangles. It's just that you have a small, a very small, and a much bigger right triangle, but they're all isosceles. So now the scale factor is much different from here to here. All right, the scale factor, guess what it is? Say a number out loud. All right. I mean, how big is 3 compared to 1? Yeah, it's 3. All right, 3 is 3 times as big as 1. So if the sides here on this one are 3 times as long, guess what the hypotenuse is? Instead of root 2, guess what it is? Yeah, it's 3 root 2. And notice in all 3 of these examples here, guys, I didn't use the Pythagorean theorem. I didn't use the distance formula. I used one fact from prior knowledge. Okay, we knew that. We knew that the isosceles right triangle with legs equal to 1 has a 1, 1, 2 ratio. And then we looked at similarity in structure to determine the other 2. And that's a major important theme in MRWC. You got to be able to see the structure between things. All right. So speaking of that, let's dig a little deeper. Now I've talked about the Pythagorean theorem before in prior lessons. So let's work with that a little bit. We're going to draw the right triangle first. Okay. So let's plot this. So 5, comma -2. So go right 5, down 2, label that A. So 5 comma negative 2. B is negative 1, 6. Go left 1 up 6. So a negative 1 comma 6. All right, and draw the right triangle. Follow the grid lines. Put the sound effects in. Okay, and connect A and B. All right, so you have this right triangle here, and you know what? Okay, I've got a computer issue right there. So from A to C, so C is at negative 1 comma 2. So from negative 1 down negative 2. So this is going to be 6 units here. 2, 4, 6, 8. This is 8. And the question is what's the hypotenuse length here? Let's figure that out. Let's use the Pythagorean theorem, right? Okay, so let's do that. So 6 squared plus 8 squared is equal to, you can call it C if you want, or you can just, we'll just call it little c. Call it C squared. So 36 plus, pause the video and complete it. Finish it, okay? Go for it. Okay, don't wait for me. All right, be a good student. Okay, and continue. All right, 8 squared is 64 equals C squared. You know, what number squared gives you 100? And the answer is 10. So 10 has to be equal to C. Okay, and you get a 6, 8, 10 triangle. So the side lengths on this triangle are 6, 8, and 10. Now, watch this. Okay, this is called a Pythagorean triple, by the way. Any set of 3 whole numbers that live on a right triangle are called Pythagorean triples. Pythagorean triples. Now, if you had a really good and strong math teacher for geometry, you should know this. Okay, so these are called Pythagorean triples, and this triple is called a 6, 8, 10, and it's a multiple of something. Okay, so I'm going to bring you back to the smallest triple that exists. Okay, so let me call these legs 3 and 4 and find the hypotenuse C. So I want you guys to work ahead of me right now. Set up the equation, find C, and then when you're ready, play the video. Okay, so on this one here, if you solved it correctly, you got 3 squared plus 4 squared is equal to C squared. You get 9 and 16 is equal to C squared. And, you know, since 5 squared is 25, if you square both sides, you get 5 equals C. Now, so that brings me to the smallest Pythagorean triple there is. It's called the 3, 4, 5. Okay, it's another Pythagorean triple. This is the smallest one. This is the smallest triple that exists on a right triangle. Now notice the 3, 4, 5 has a similarity between that and the 6, 8, 10. Okay, so if I put 6, 8, 10 underneath it here, what do you notice? What do you notice? What do you do from the first triple to get to the next triple? Yeah, you simply multiply it by 2. It's called a multiple of the first. It's a multiple of 2. Okay, so you just multiply all the 3, 4, 5 by 2. You double all their values, and you get another triple, 6, 8, 10. And you could triple a triple if you want. You'll still get a triple. So if you triple a triple, you get a 9, 12, 15. Okay, so a 9, 12, 15 is another Pythagorean triple, which satisfies the Pythagorean theorem. Okay, so these are called multiples of each other. That's what I meant by this word right here. If you didn't know that in the beginning, well, you just learned something. Okay, now another Pythagorean triple that you kind of need to know that's very, you'll see it in pre-calc quite a bit, and you'll see it later on, is the 5, 12 something. I'm not going to tell you what the something is. So let's figure it out, okay? So let's set up the Pythagorean theorem. 5, 12 plus 12 squared is equal to C squared. Pause the video. Go ahead and solve for C. Okay, I'm going to assume that you did that now, if you're a good student. Okay, so when you work this out, you get 25 plus 144, which is 169, is equal to C squared. And then if you square root these bad boys like this, you get 13. All right, the square root of 169 is 13. And so we have another triple. So your triple in this case is called the 5, 12, 13. So now we have three main triples, two main triples, and their multiples. Okay, the multiple of a 3, 4, 5 is 6, 8, 10. So don't think that really 6, 8, 10 is a unique triple. It's just a multiple of the first one. And so another triple, if you take the second multiple of the 5, 12, 13, you get 10, 24, 26. Okay, yeah, if you multiply that by 2, so you get another triple, but it comes from the 5, 12, 13. So the 3, 4, 5 and the 5, 12, 13 triples are the two smallest triples that exist, and then there are a bunch more. Okay, and in fact, there's an infinite number of triples, so that can be proven too. And that right there is a little lead into what's called Fermat's theorem. So you can research Fermat's theorem. He's famous, okay, famous Italian mathematician from the past, relating to the Pythagorean theorem. Okay, not about the Pythagorean theorem, but relating to the Pythagorean theorem. Oh, you know what? And you know what? I didn't say it exactly correctly. So, anyways, it's related to the Pythagorean theorem. I know that for sure. Okay, and there's a whole book written on it. It's pretty awesome. All right. So in MRWC, a couple things that you need to be really good at. Okay, you need to be flexible. Okay, I love this word. And I'm going to put in caps too. Flexible. All right, with the following. Okay, so this is important. Okay, you need to be flexible with methods. There are different ways of doing things. So, and we're going to be analyzing this in the next activity, 3B3. So this is actually an important part of getting you guys ready for 3B3. This is the prep for activity 3B3. Okay, so pay attention here. You need to be flexible with different types of numbers. You need to be flexible with radicals and roots, and there's because we're going to get into a huge discussion about them, and it's not easy in the beginning either, so it's deceiving. So you better put your heart and soul in this, because this is not easy for a lot of people. I know just because I've worked with students over the years, so believe me. So, and you also need to be flexible with the different type of operations. Okay. Now, having said that, you also need, all right, to be able to see the structure. So I'm going to put that in red too. So this is a major theme in this lesson here, because we want to get you ready for the future activities and the future things we're going to be doing. And seeing structure in things is important. So for example, structure in the Pythagorean triples, I'm talking about the 3, 4, 5 first triple. That's the smallest triple that exists. All right, there's your structure. So if I told you, if I gave you a triangle here, and if I label this 5 and I label this 4, all right, and then I said it's a right triangle, and I asked you what the third side is, you know it has to be 3. If I said, okay, the two sides, this is 5 and this is 3, and I ask you to find the third side, well, you know it's 4, because you know the structure of the first triple. You know the structure. That's what I mean. All right, so you have to be able to see how things are related, and one of the important things is looking at triples. I'm talking about the Pythagorean triples. And another one is the one that we talked about up here, which is the 5, 12, 13. So for example, if I give you this triangle, and I put a 5 here and a 13 here, and I asked you to find the unknown leg, okay, it's 12 just by knowing the structure. Or if I drew it again and I drew this one, okay, and I said this is 13 and this is 12, and I said find the short leg. And so whether I ask you to find the long leg or the short leg, it's easy. Why? Because you know the structure. You know the Pythagorean triples, at least the first two. And out of, there's an infinite number of them, but at least you know the first two. So you got to be flexible with methods and numbers and roots and operations, but you also have to be able to see things and how they're structured. So that's really important. All right, now let's get into radicals and roots. Okay, so this is where the numerical part comes in, and this is not easy in the beginning for a lot of people. So this is a big example right here. Okay, so let's get involved with what's called the distance formula here. So let's put it in red. So let's write down the distance formula here just so you can have it in your sights. And especially if you don't have it memorized from back in the day. So it's x2 minus x1 quantity squared plus y2 minus y1 quantity squared. There's your distance formula. Okay, so you have your x values first, so x1 comma y1 first. You have your next coordinates, x2, y2 second, first point, second point, and so on. Now, before in our first activity, I said line them up. If you want to do that, you can. Okay, you can go, 5 rad 2, comma, 2. And then this is point A and point B. You get 3 rad, it says 3 rad 2, comma, negative 2. So if you want to line them up, you can. Okay, just like we did in the very beginning. Okay, if that helps you. So here we go. I'm going to find the distance between A and B. All right. So we're going to subtract up. We're going to take the second coordinate minus the first coordinate. So subtract up. I'm just going over all the basics in our first lesson a week or two ago. Okay. So you take 3 root 2 minus 5 root 2. Or you could, organize them the other way and subtract down if you want. It totally doesn't matter. So 3 root 2, all right, minus 5 root 2. All right, quantity squared plus, and then the y2 minus y1, so negative 2 minus 2. And then you go for it. So on this case right here inside the root here, these are like terms. Why? Because they both involve root 2. It's not like one involves root 2 and the other one involves root 3. They both involve root 2. So all you do is subtract the coefficients. I'm talking about this one and this one. Right? 3 minus 5 is negative 2. So you get negative 2 rad 2. So notice that I just took a look at the 3 and then the minus 5 gives you negative 2. And you got to square that, of course. And then negative 2 minus 2 is negative 4. That's simple. Okay, and then here's the critical part. So when you square a product, now this is a product. I'm going to put a dot right here. Okay, when you square a product, you got to square both terms. So just this is what I'm saying. The square of a times b is equal to a squared times b squared. That's an exponent law. It's called the product rule. So when you take a product to a power, you just square both factors. Okay, so you got to square the negative 2 and you got to square the root 2. When you square the negative 2, you get 4 times the square root 2, which is 2. Notice I put a dot there for times. When you square the negative 4, you simply get 16. And then 4 times 2 is obviously 8, and you get, so you get 8 plus 16, and that's square root of 24. And then let's take it up here. So the square root of 24 is equal to the square root of 4 times the square root of 6, which is 2 rad 6. That process is called simplifying. So you square root the factors, as I said in prior lessons. So square root both factors. Step 1 right here. Step 2, you simplify what you see. Okay, and the square root of 4 is obviously 2, so you get 2 root 6. So here, when I say you got to be flexible with radicals, I'm talking about roots. You have to be able to square right here. This is in the second step right here, a square product. And the way you square a product, let's see here. You got to, when you square a product, something times something here, you got to square both of them. All right, keep that in mind. All right. So you got to be familiar and you got to be good at roots, and you got to be good at your exponent rules, and you got to be good at squaring. Squaring comes in the Pythagorean Theorem, and it comes out in the distance formula, which is based upon the Pythagorean Theorem. So you got to be good at that. Another thing you got to be good at is seeing the structure in algebraic expressions. And again, highlight the word structure. Here we go, and don't work ahead. Do not work ahead. You're going to be doing a lot of erasing, because I'm going to be doing things a little differently here. Perhaps. So just go slow, pay attention, and learn something. All right, so here we go. So we got 4x, which is 4 times x minus 24, and you got to factor out the GCF, which is, something from grade school. It's called the greatest common factor. So the greatest common factor. All right. So when you do that, there's different ways to think about it, but one way to do it is you take 4x minus the factors of 24. Now, factors of 24 are obviously 1 times 24, 2 times 12, 3 times 8, 4 times 6, and, 6 times 4, and the list goes on. So there's only 4 factor pairs. These are called factor pairs. Okay, for obvious reasons. They're factors and they're pairs. Pair of numbers. Okay, so what you want to do is you want to find the greatest common factor. So the only one that deals with another 4 is 6, or 4 and 6. So I'm going to write 24 as 4 times 6. And so notice they have a common factor of 4. Well, then factor it out. Okay, so it's going to be 4 times something. Well, 4 times what? Well, let me use black here. So this is equal to 4, there's your common factor, all right, times what? Well, the remaining factors, x minus the 6, and that goes in here, all right, x minus 6. How do you check? Well, you distribute through, just like you normally would. 4 times x is 4x. 4 times 6 is obviously 24. So you factor out the GCF right there of 4. Now, what's the GCF of 3, root 5, and root 10? Well, in order to see that, you have to split the root. So root 10, all right, is nothing more than root 2 times root 5. Okay, you got to split the root. Okay, you got to square root the factor. So the square root of 2 times the square root of 5. And now you see the common factor. It's got to be root 5. That's the only factor they have in common. So let's factor it out. So you factor out the root 5. And what do you have remaining? Well, you have 3 plus rad 2. All right, so 3 plus rad 2. And that's called factoring out the GCF, or factoring out a common factor, however you want to say it. So there's different ways of doing things. This one here, there's different ways of doing this. You could simplify first. If we simplify rad 20 as root 4 times root 5, we get 2 root 5. If we simplify the square root of 45, we get the square root of 9 times the square root of 5, which is 3 rad 5. So that process is called simplified. So some people in this case right here, if they see something like this, we go, okay, you can't combine them because the radicals are different, the roots are different. One's root 20, one's root 5. They're unlike. All right, so rewrite them. So this is equal to 7 times 2 rad 5 plus 3 times the 3 root 5. Once again, I simplified root 20 to 2 root 5, and I simplified rad 45 to 3 root 5. I did that all on the side in the margin. Okay, so let's simplify further. So 2 times 7 is obviously 14, so you get 14 rad 5 plus 9 rad 5. And if you add 14 and 9, okay, you have to add the coefficients. 14 and 9 gives you 23, right? So you get 23 root 5. So you add like terms. Add like terms. You add the coefficients. Okay, all you do is add coefficients. And if you guys don't know what coefficient means, well, it's the number in front of the root, okay? Just like the number in front of the variable is called the coefficient, like up here in part A, 4 is called the coefficient of x. Well, 14 is the coefficient of root 5, 9 is the coefficient of the other root 5. And if you have 14 root 5s and 9 more root 5s, well, you have 20 root 5s in all. Okay, you simply count how many you have. That's all you do. Okay, you're going to need to go back to Algebra 1. There's a lot of Algebra 1 work in this unit here, and you've got to be good at it. And one's called the difference of squares. And why is a minus b times a plus b called a difference of squares? I don't know. Well, I mean, I do know. So let's let's use FOIL, or the distributive property. Distributive property, or commonly known as FOIL. It's an acronym standing for the same thing, but the technical property is called distributive property. So let's multiply out. So a times a was usually a squared. A times b is ab. And then negative b times a is a negative ab. Notice I switched the order there. B times A is A times B. Okay, the order in multiplication doesn't matter. And then negative B times B is a negative B squared. Okay, so what do you get? Well, you get A squared minus B squared. So this is called a difference of squares. Because it's a difference means minus, okay, and A squared and B squared are squares. So it's called a difference of squares for obvious reasons. All right, difference means subtract, and when you square something, it's called a square. So A squared is a square, B squared is a square. Hopefully that's obvious. Okay, so let's go. Let's do it. Now, instead of using FOIL, you use the structure, okay? You use structure. So use structure, all right, instead of FOIL. Instead of FOIL. So don't work ahead. All right, so this is A minus B, and this is A plus B. So I see that one's a sum, one's a difference. So all you do is square both and subtract. That's all you do. Let's write that down. Square both and subtract. Square both and subtract. This is a major deal right here. I know all these little things coming from Algebra 1 seem like no big deal, but you're going to find out that they are. Okay, so what do I mean? So you got to square both. So take 5x squared, notice that I put in parentheses, and takes 2 squared. Well, 5x squared is 5x times 5x, or 25x squared. 5 squared is 25, x squared is x squared. You got to square both terms inside the parentheses. So that's what I mean by you got to get good at all these basic properties. And obviously 2 squared is 4. So notice that I didn't use FOIL. I didn't multiply 4 times because the middle terms will always cancel out. This AB minus AB here always cancels out. Your instructors might have done that. It might have canceled out to 0. So why go through the 4-step process of FOILing when you can just square both and subtract? It's just too simple. So you gotta learn the structure of things. All right, this is also the same structure. It's A minus B times A plus B. So the structure is the same. So all you do is square both of them and subtract. So you take the root 5, square it. You take the root 2 and square it, with or without parentheses, doesn't matter. All right, you square the root 5 to get 5. You square the root 2 to get 2, and 5 minus 2 is 3, and you're done. And when you get good at that, you just do it in your head. Okay, so like on the third one here, you get A minus B times A plus B. It's the same structure. All right, so this is equal to root 7 squared minus root 3 squared, which is just 7 minus 3, or 4. It's that simple. But it's not that simple unless you see the structure. So once you see that it's a difference of squares, you don't use FOIL. You don't multiply out 4 times. You want to think more efficiently. You want to do things quicker by looking at patterns and structure and things like that. And that's what this chapter is about, is by looking at the patterns and the structure on things versus just being a robot, if you will, and just do the algebraic properties like distributive property all the time. Like here, okay, if you don't know how to square binomial in your head, well, then you work it out, okay? So, but there's an easy way to do it rather than working it out. And the most common mistake people make is that they just square both the terms in the sum and they get the wrong answer, okay? Because A plus B quantity squared, let me make a little note here, A plus, come on, Ainsworth, A plus B quantity squared does not equal to, all right, A squared plus B squared. Highlight that. This is a common mistake. Common mistake. I see it all the time, even all the way up to the calculus ranks. Okay, so those are not equal. All right, so A plus B times A plus B. So let's multiply out. So A squared, okay. A times A is A squared. A times B, obviously AB. And B times A, AB again. Oops, gotta spell it right. Okay, there we go. I'm going to put another plus sign because B times A is A times B, right? And I write it the same way because a lot of people think that B times A is different than A times B, and it's not, because the order doesn't matter in multiplication, right? Plus B squared, and so you get A squared plus 2AB right? You add their coefficients. Whoops, 1ab and 1ab is 2ab, right? Okay, and then plus b squared. So this right here, this tells me, if I'm going to interpret this now, is it means that this means square the first term, square first term. This right here tells me to multiply and double. Multiply and double means times 2. Double, you know, whenever you see this times 2, that means double it. And this tells me to square the last term. Square last term. So the way I remember to do this when I was a kid, and ever since then, is square, multiply, double, square. Square, multiply, double, square. Now, you got to be careful here because I'm abbreviating. So, and these are not minus signs, they're hyphens. Okay, so it's just a square, multiply, double, square routine in your head. So when I do this here, I take x and I square it. I multiply the two. 7 times x is 7x, but then I double it to get 14x, and then I square the 7 to get 49. And notice that I didn't write it out. I square, multiply, double, square. That's all I do. And then on this one here, you got to be careful. When you square the 3x, you get 9x squared. Minus 3x times 4 is negative 12x. And negative 12x double is negative 24x. And then you square the last to get positive 16. So you square, multiply, double, square. You probably should highlight that because that's how it's going to, that's how you square a binomial. When you square the 5y, you get 25y squared. You multiply the 2, 5y times negative 1 gives you negative 5y, but when you double it, you get negative 10y, and then you square the last. And whatever you square is always positive, remember that. So you square, multiply, double, and then you square. And it's a 3-step process here. So you square, multiply, double, square. All right, and you'll have to get good at that through practice. All right, so that's the prep involved in activity B3, 3B3. And what you're going to do is analyze the methods from 2 people. You're going to analyze Anne's solutions right here, and then you're going to analyze Simon. So how are they similar? How are they the same? So you're going to compare them. So Anne and Simon use different methods, okay, to simplify their homework problems. Both methods are correct, so keep that in mind. All right, and their answers match. Simon thinks his methods are more efficient. Okay, now efficient, the word efficient, that can be interpreted a couple ways, but when you're more efficient, that typically means, all right, less steps, okay, could mean that. And it also means it's typically easier too. So more efficient and perhaps even easier. Okay? But typically it means less steps in the total. You're going to see that. With your partner, work through both Anne's and Simon's solutions for each expressions and compare the 2 methods. All right, you want to compare. So this takes some really some in-depth analysis. You got to go through each one, and you got to figure out and understand each one. So really important here, you have to understand, okay, every step of each method. Every step of each method made by the students. Now let's just look at it right here. This is it's a big activity here. So we have 5 problems and we have 2 people. So you got to analyze 4 problems total. Okay, you got to analyze all 5 problems for Anne and then compare it to all 5 problems for Simon. You got to compare which one's more efficient, which one's easier, which one is using structure, which one's not. Okay, so who's using structure versus just steps? You know, just like distributive property lesson. Who's using structure? Who's being efficient? Okay, so in fact, let me write that down. So who, you know, I'm talking about Anne and Simon here. Who is using, all right, structure? Got to think about that. Structure. All right, who is being efficient? Who's using structure? Who's doing things the quicker way? And remember, structure like this right here, like the difference of squares, for example. Okay, who's using that technique? Or who's squaring a binomial efficiently, like just by square multiply double squared technique versus multiplying 4 times every single time? I can tell you that people that are very good mental math and that can look at an instructor and just follow along with a lesson, know structure and know patterns and know how to do things in their head, like how to square a binomial in their head, or how to see that this product of the difference of squares, these product of each one of these binomials here, is just a difference of squares. Students that know structure and things like that are going to do well later on in advanced courses like calculus, for example. Oh, guess what? They have 6 and 7 problems here. So they actually have 7 problems. So you're going to have to analyze 14 total problems because there's 7 for each person. All right, and then we're going to have a discussion on each one. So make notes in the margins. So use the margins for notes. So use margins for notes. Okay, and annotate it and see what's going on, and use your highlighter and see who's using structure and talk with your group. Okay, and then when we come back together in the main classroom, we'll talk about that as a class with me involved. All right, this is Mr. Ainsworth. I will see you after this activity, and we'll discuss your results and your thinking. See you soon.